Assalamualaikum and good afternoon. Boleh dengar tak?
Boleh, boleh.
Testing suara. Boleh? Alright. Mechanical separation. Uh, for the slide, you can refer to elite. Yeah. For books, I'm using the two books. The Warren Mackie. This is book number 2 or number 1. I don't remember. But the book is available in ebook. Another book is this. No, okay. Okay. This stage of this as part process and separation process visible. So I'm going to prepare the slide. It's based on these two books. So mechanical separation. So mechanical separation, we start with books. Over the cap. Book 1, book 2, chapter 30, page which picture. In PDF, it's 1015. Okay. See you the top there. Oh, screening. Screening is a method of separating particle according to size alone. So this is physical separation or mechanical separation in has to meaning the solid drop on and throw against spinning surface. So keyword is the undersize or fine pass through the spin opening, the oversize or tails did not go through the spin opening. So it's a mesh. Macam separapis. It is a spinning. So bigger particle cannot pass through the spin because of the size. So we call it oversize. Tails. For those who can pass through the mesh is undersized because it's smaller than the mesh. So call it fine. So you know, because particle drop easily through large opening in a stationary surface. Okay. Such opening in a stationary surface, but with fine particle, the screen surface must be agitated in some way, such as shaking, vibrating its mechanically. Yes, vibrate to allow the spinning. Example of what is this? Stationary spin or grizzlies. So the grizzly is a grid of parallel metal. This is a grizzly that time stationary spin. The slope and the path of the train are usually parallel to the length of the bars. So very prostrate was from the release pressure on the upper end of the grid. The comparison of ideal and actual screen. The objective of a screen is to accept a fit containing a mixture of particles of various sizes and separate it into two fractions and underflow. This is another word that you need to learn. So you will learn about fine, undersize, underflow. So all of this. So this keyword representing particle that pass through the screen. Then another keyword is the overflow. Overflow, oversize, or tails. So this one is rejected basically meaning the size is too big to go through the mesh. An ideal spin would sharply separate the fit fixture into such a way that smallest particle in the overflow would be just larger than the largest particle in the underflow. Such an ideal separation defines a cut diameter DPC that marks the point of separation between the friction. Usually, DPC is chosen to be equal to the mesh opening of the screen. Uh, Supernatural valid can be written. This is from the book. More one big over a scale which are useful in calculating the ratios of heat, oversize, and underflow from the screen analysis of the true stream and knowledge of the desired cut diameter. So let F, D, and B be the mass flow rate of the feed, overflow, and the underflow. So XF, XD, and XB be the mass fraction of material A in this three stream. The mass fraction of material B in the feed, overflow, and underflow are 1 minus XF, 1 minus XD, and 1 minus XB. Okay. So, because there are two material, A and B. So if you minus 1 minus XF, then it's equal to mass fraction of the material B. So since the total material fed to the spin must leave it either as underflow or as overflow, the metal A in the feed must also live in this fluid stream on Fxf equal to dxd plus dxp, efficient 3.2. So if it's material B, so F equal to, sorry, F1 minus XF equal to B1 minus HB plus B1 minus HB. So after this one, the equation of V, coefficient of equal 1, equal to GP over F. So D over F is what we call ratio of fit, ratio of D equal to overflow. So ratio of overflow to feed. D is the underflow. This one. Okay. Equation of D equal. So F is feed, reflection of feed. So F is of feed, D is overflow, B is the overflow. Now the spin effectiveness, the effectiveness of the spin, often called spin efficiency, is a measure of the success of the spin. Is closely separating materials A and B. If the spin function perfectly on of material A, would be in the overflow, and all of material B would be in the underflow. So that is 100% B lah. The common measure of spin effectiveness is the ratio of oversized material A. That is actually in the overflow. The amount of A is with the heat. This quantity are dxf and fxf to 3.5, where EA is the spin effectiveness based on the oversize. So oversize, what else? Overflow or there. So really, an effectiveness EB based on the undersize material is given by EB equal to, okay, this equation 20.6. Combined over effectiveness can be defined as the product of the two individual ratios. And if this product is noted by E, so E equal to EA times EB equal to G of this equation, substituting D over F from 30.3 to 30.4, this equation, you get 30.7. Yeah, 30.7. This is 30.7. Can you use this equation? Yes, can as well. Yeah. So E efficiency is equal to EA times EB equal to this expression. Or you can use the mass fraction. Again, depend on that question. Example. A quartz mixture having the spin analysis shown in table 20.1 is built through a standard 10 mesh screen. The cumulative spin analysis of overflow and underflow are given in table 20.1. Calculate the mesh ratio of the overflow and underflow to fit and the overall effectiveness of the screen. So we have this is the mesh. The bigger the number of the mesh, the smaller the mesh, the size of the mesh. Okay. So mesh 4, this is mesh 3, so mesh 6. Everything goes to the everything goes to the overflow. Okay. Let's see. The cumulative analysis of heat overflow and water overflow in 2023. The cut one diameter is the mesh of the screen, which from table 21 is 1.61. This is 6.651 mm for mesh 10. So from table 21 for this screen. So for this screen, the XF is 0.47. So XD is 0.85, XP 0.195. So from this equation 30.3, from the equation 30.3, the ratio of overflow to feed, so we get 0.42. Ratio of underflow to feed. You can also use equation 30.4 or just subtract 1 minus d over f. You get 0.58. This is underflow to feed, ratio underflow to feed. So the overall effectiveness from equation 30.1, sorry, from 50.7 is for this equation, you can get the effectiveness. Our effectiveness is 0.669. Percent, 6%. 6% effectiveness. I got an exercise, but not sure how to do this. So a quartz mixture having the spin resistance equivalent to equal 1. A similar question but different value. 28 mesh spin. The key data is from 30.1, so table 30.1. So here how to do this? So identify the XF, XB, and XB. XF 0.94, XP1, XP 0.91. So from here, you identify the overflow, ratio overflow to heat. We go to this one. Then ratio of underflow to heat. Then using 50.7 to obtain the overall effectiveness of the screen. Some of the question. This slide is simplified. So for the filtration, normally full class is very long. You learn about how the membranes work theoretically, but I limit to just cake filter. So filtration is the removal of solid particles from a fluid by passing the fluid through a filtering medium or septum in which the solid are deposited. So what happened during the filtration? So the medium is liquid, but inside the liquid there's a solid particle. Normally we have organic material inside. So this water, sorry, liquid, when in contact with the filter, so the liquid can pass through the filter. So the idea is similar to the screening. Those particles that is larger than the pores that we can find on the filter will not pass through, but those who smaller than those size will pass through along with the liquid water. So those who cannot pass the filter, it will form another thing like the cake filter. So the cake filter separates between large amount of solid as a cake of crystal or sludge. So what happens when you have a filter? The maybe first few hours, few days, the membrane is doing the filtration. After some time, there will be say, a sedimentation that to the surface of the membrane or filter. So this newly formed uh, material, normally an organic material on top of the filter, it accumulate then it's accumulate then um, after some time it's look like a cake. So this cake filter is actually can filter can can be a secondary filter to the actual filter, which is good. But drawback from this is the flux. We call it flux. The flux is the amount of water can pass through the membrane or filter. Since we have uh, theoretically two filter, one is the actual filter, the other one is the cake filter. So the energy required for the water or the liquid to pass through is higher, which incur cost for the pump, and the amount of water that we can collect is lower because of the two in one filter. Yeah. Then we have a clarifying filter with a small amount of solid to produce a clean, fast, sparkling, clear liquid such as beverages. The solid particle trap inside the filter. Let's see come down. But you can refer to the books one for this. You want to know more? It's like this. This is the cat, this is the medium. This is the clarifying filter, this is the cross flow filter. So the clarifying filter, another word for it is the what do we call it? Close close end filter because the water coming in, then the filter will have to filter the medium. For the cross filter, there's a pressure difference, but the water, the feed is always flowing in parallel to the membrane filter. So in a cross flow filter, the saturation flow the pressure at a fairly high velocity. So here is a high velocity to create the pressure difference for the water or the liquid from this uh, feed area to pass through. So the pass through, then we call it permeate or filtrate. Those who cannot pass through here, only we call it retentate. So over time, the retentate will be increasing in concentration. Some of the material cannot pass through, only the liquid can pass through. So a thin layer of solid may form on the surface of the medium, but the high is to keep the layers from being absorbed. The good thing about the cross flow filter, the cake that form on a normal filter, it's relatively, you can say, yes, it will be there, but it's not as much as the very filter. So for the open-ended, sorry, for the close-in filtration like this or clarifying filter, after some time there will be a cake. So this cake is the cake. Oh. Mm. Oh, this is a filter press. Filter press contains a set of plates designed to provide a series of chambers or compartments in which solid metal. The plates are covered with a filter medium such as canvas. Slurry is admitted to each compartment under pressure. Filter passes through the canvas out of discharge pipe, maybe with a wet cake or solid line. So what happens here, you fill in the filter. So this type of filter, we call it a flagship membrane. So going in, then there's a force to create the pressure difference between the membrane and the incoming heat. So this pressure difference allow a liquid to pass through the membrane. So so it's similar to the theory that you just learned. So in order for the liquid to pass through the filter, you need to create this pressure difference. So for ultrafiltration, normally the pressure difference is low, like one to two bar is enough. For filtration, normally we need like 8 bar Then for the reverse osmosis, it's quite high, like 16 to 20 bar easily. Yeah. But for the reverse osmosis, it's very good. But normally we didn't use reverse osmosis like that. Normally they have this a set of pre-filter pre-treatment before it goes to the last uh, unit operation, which is the reverse osmosis to separate the salt for the desalination uh, uh, project system. Is it called active filtration? And we put people with the overall pressure drop at any time is the sum of the measure drop over medium and kick. If VA is the inlet pressure, PB the outlet pressure, and P prime the pressure at the boundary between kick and medium. So we have delta P equal to PA minus PP equal to PA minus P prime plus P prime minus PP equal to delta PC plus delta PM. Delta PC pressure drop over the kick, pressure drop over the medium. So the medium equal to the actual filter, then we have pressure drop over the kick. Two things. Settling and sedimentation. This is based on book number 2. Book number 2, you can refer to this paper. So, 4 to 2, chapter 30. Theory of particular nature of weight. For rigid particle moving in the fluid, there are two forces acting on the body. The gravity acting downward, buoyant force acting upward, and resistance or drag force acting in the opposite direction to the particle motion. The three forces acting on the rigid particle moving in the fluid. This is buoyant force, gravity, and the resistance. So we will consider a particle of mass m, kg falling at velocity v, meter per second relative to the fluid. The density of the solid particle is rho p, kg per meter cube solid, and that of this liquid is rho kg per meter cube liquid. The buoyant force FP in meter is if we go to m of g over rho p equal to v p rho g. So m over rho p is the volume, Vp in meter cube of the particle. G is the gravitational acceleration in meter per second squared. So Fb equal to Vp rho g. Gravitational force, external force on the particle, because there are three force acting toward the particle moving in fluid. So gravity is Fg equal to mg. Another one is the drag force. Ft on body in Newton may be derived from the fact that as in the flow of fluid, the drag force frictional resistance is proportional to the velocity head v square over 2 of the fluid displaced by the moving body. This must be multiplied by the density of the fluid and by a significant area A, such as the projected area of the particle. This was defined previously in equation 6.1-2. So Fd equal to Cd v square over 2 log A, where the equation Cd is the proportionality constant and is dimensionless. Ini dapat Cd. Oh ya, Cd. So the resultant force on the body is then Fg minus Fp minus Fd. This resultant force must equal the force due to acceleration. So mdv over dt equal to Fg minus Fp minus Fd. Substituting 30.1.1 to -3 to -4, we get 30.1-5. So 30.1-1, 30.1-3. The one is referred to the equation that previously. The three force acting on the particle moving in the fluid. So we have 30.1-5. If we start from the moment the body is released from the position of the rest, the body falling consists of two periods, the period of accelerated fall and the period of constant velocity fall. The initial acceleration period is really very short, on the order of a 10 or second or so, hence the period of constant velocity fall is the important one. The velocity is called the free settling speed or the terminal velocity. Yeah, constant. Or the highest velocity it can be. Yes. But to solve for the terminal velocity in equation 2.1-5, so dv equal to dt equal to 0, the equation becomes 2.1-6. So for spherical particle, m is equal to this equation, and a equal to pi d square dt over 4. Substituting this into 30.1-6 for spherical particle, we obtain Vt equal to 30.1-7. Vt is, okay, what is the density, gravity, and this is diameter. Yes, diameter of the particle. So, an assumption. Next is drag coefficient for rigid sphere. The drag coefficient for rigid sphere is shown to be a function of a Reynolds number. So dp d rho over mu of the sphere is shown in 30.1-1 in the laminar flow region, called the stroke flow region, for NRE less than 1. So the drag coefficient is 30.1-8. CD equal to 24 over NRE. So NRE refer to this equation, where mu is the viscosity of the liquid in Pascal per second or kg per meter second. So to do this with 30.1-7 for laminar flow, we get 30.1-9. This equation. This is for the laminar flow. So how you know laminar flow? You need to do the sum calculation to confirm that the NRE is actually more than sorry, less than 1. Then we have this figure 30.1-1. So drag coefficient CD is the NRE for the x-axis. So CD equal to 24 over NRE. So this is the lamina. Okay. Lamina. How do you know lamina? Because of the NRE less than 1. Sudah kuasa 1 ya. Less than 1. Instant. Dia kuasa masuk. For other shape of particle, the equation will differ from those given in 30.1-1 and that are given in the 6.1-2, where in the turbulent Newton law region above a real number of about 1,000 to 2 times 10 to the power of 5, the coefficient is approximately constant at CD equal to 0.4. So for turbulent region, how do you know turbulent region? The real number is big, greater than 1. So automatically the CD is approximately equal to 0.44. Solution of equation 30.1-7 is by trial and error when the particle diameter is known. And the terminal state is to be obtained because CD also depends upon the resistivity. If the particle are quite small, Brownian motion is present. Brownian motion is the random motion imparted to the particle by collision between the molecule of the fluid surrounding the particle and the particle. This movement of particle random motion tends to suppress the effect of the increased resisting of the particle will occur more slowly or not at all. At particle size of a few micrometers, the Brownian effect becomes appreciable, and at size of less than 0.1, effect is predominant. For very small particle, application of centrifugal force have reduced the effect of Brownian motion. So to reduce the Brownian motion, we need to make it kacau. What's up, Brownian motion? Brownian motion, you know what? Then we see it in asap, in smoke. It's getting, you put powder on the surface of the water. It's started to move. The move is random, but it's not sure if it's random. There might be a equation representing Brownian motion. Example 30.1-1, setting velocity of oil droplet. Oil droplet having a diameter of 80 micrometer or 0.02 millimeter to be settled from A. The temperature of 37.8 degrees C and 101.3 kilopascal pressure. The density of the oil is 900 kg per meter cube. Calculate the terminal settling velocity of the droplets. The various known dP equal to 2 times 10 to the 105 m droplet diameter of the oil droplet, 20 micrometer. Rho P equal to 900 kg per meter cube. From appendix A3, you can refer to the books. Belakang. For A at 7.8 degree C, the density of A at 37 is 1.127 kg/m3. Mu equal to 1.9. This is the viscosity. The droplet will be assumed to be rigid sphere. That's another problem. Okay, this question already asked. Do you think early this year for your early this year? For unit operation for the final exam. The solution is trial and error since the recipe is unknown. Hence the CD cannot be directly determined. The real number is as follows. So calculator the real number using the T.1-10. VT that out. Yeah. So NRE 1.197 VT, which is why it's a trial and error. For the first trial, so then assume that VT equal to 0.305 liter per second. Then the NRE, because the NRE is 1.197 VT, now VT is 0.305. The substitute, we get NRE equal to 0.365, which is lamina is less than 1. Substituting into equation 30.1 solving for CD, like this one. So CD, so VT equation CD is not available. Okay, CD also in VT. This is 30.1-11. CD equal to 0.2067 over VT square. VT is this, we assume. So CD equal to 2.22. Next is assume again the VT is 10 smaller than the previous VT. So this one is 0.0305 liter per second. Substituting into this equation NRE, we get 0.0365. CD using this equation 222. Then another trial is VT 110, lower than I think 10 lower than the second trial. CD is 22200. NRE very small. So this three value weighted for NRB and CD are plotted on a graph similar to 30.1-1 and as shown in figure 30.1-2. So 30.1-1 is this one. So since now you have the value word, three value of CD, three value of NRE. So plot it here. Something like this one. This is the 3 point from your calculation. So the intersection is here. NRE equal to 0.012. Okay. So the velocity can be so 0.012 is coming from the figure 30.1 dash 1. The velocity can be written from the random number in equation. Okay. Then you determine the actual value of VT. So this actual value of Vt, you substitute into the question 30.1-9. Ada dua cara. Alternatively, the density can be weighted by using equation 30.1-9. Okay. Either you use this method or this method. Note that equation 30.1-9 could not be used until it was determined that the particular wall was in the liminal. So before you can use 30.1-9, you need to calculate the NRE, make sure it is below the one, the nominal region is the flow. Okay. When you go start. All right. Now you refer to books. Partner part. Differential settling and separation of solid in classification. Sink and float method. Device for the separation of solid particle into several fractions based upon the rate of flow of settling to fluid, known as classifier. There are several separation methods for accomplishing this, namely sink and float and differential settling. In the sink and float method, a liquid is used whose density is intermediate between that of the heavy or high density material and that of the light density material. In this liquid, the heavy material will not float but settle out from the medium while the light particle will float. So this method is independent of the size of the particle and depend upon only upon the relative density of two materials. This means the liquid used must have density greater than water, since most solids have high density. Unfortunately, few such liquids exist that are cheap and non-corrosive. As a result, pseudo-liquids are used, consisting of a suspension in water of a very fine solid material with high specific gravity, such as galena and magnetite. So Hg 7.5, this one, particle 1.7. Inner setting is used, and the bulk density of the medium can be weighed widely by varying the amount of the fine solid material in the medium. The common vision of systemic are concentrating all material and cleaning the core. The fine solid material in the medium are so small in diameter that their settling velocity is negligible, giving a relatively stable suspension. Another method is the differential settling method. The separation of solid particle into several size fractions based upon the settling velocity in a particular medium is called the differential settling or classification. The density of the medium is less than that of either of the two substances to be separated. In differential settling, both light and heavy materials settle through the medium. Later I put in the slide. Disadvantage of this method if the light and heavy material both have a range of particle size that is smaller heavy particles settle at the same terminal velocity as larger light particle. Suppose that we consider two different materials, heavy density materials such as galena and the light density materials such as quartz or silica, quartz. The terminal frequency of column A and B from question 30.1-7 can be written as 30.1-20. This is for material A, component A. In this case, galena. Component B is quartz or silica. For particle with equal setting velocity VTA equal to VTB, and we obtain by equating equation 50.1-20 to 50.1-21, cancelling term and squaring both sides, then we get 30.1-22 or 30.1-23. So the assume particle equal setting must be VTA and VTB, although it have different specific gravity. For particle that is essentially sphere at very high number, in the turbulent Newton law region CD is constant. So CD for the high turbulent Newton law region is equal to 0.44, right? Yeah, 0.44. So in this case, CDA is equal to CDB since they are sitting at similar velocity, leaving 30.1-24. For laminar stock law settling, CDA equal to this expression, CDB equal to this expression. Substituting question 30.1-25 into question 30.1-23, arranging for Stokes law where VTA, this is referred to the velocity of the setting for component A and component B. So we get 30.1-26. For transition flow between laminar and the turbulent flow, we have 30.1-27, in which the n is 0.5, between 0.5 and 1. N here refer to this. Okay. So this is for the transition flow between laminar and turbulent. This is for the Stokes law or laminar region. So the settling between material A and material B okay, so metal A, metal B. Metal A is galena, B is the quartz or silica. This is the velocity. This is the diameter of the particle. So for settling in the turbulent range, equation 30.1-24, 30.1-24, this equation. All for equal settling velocity particle where dPA equal to dPB. This is refer to the diameter of the particle. And setting is in the turbulent region, following equation 30.1-20 and 30.1-21. Then we get 30.1-28. This is referred to the setting velocity. So if both A and B particle are settling in the same medium, then equation 30.1-30.24-28 can be used to make the plot given in 30.1-3 for the relation of velocity to diameter for A and B. So 30.1-3 is referred to this figure. Because it's the settling in the same medium, then we can plot the figure. First, we consider a mixture of particles of material A and B with a size range of dp1 to dp4 for both types of material in the size range dp1 to dp2 integer to dp1-3. A pure fraction of substance B can be obtained since no particle of A settle as slowly. This is need to refer to figure 3.1-3. Oh, yes. With an AB with a DP1. In the session DP1, yes, this is DP1 to DP2. DP1, DP2. In this figure, a poor fraction of substance B can be obtained since no particular settle S slowly. Okay. Hopefully you understand. So for the DP1 to DP2, only particle, only a pure fraction of substance B can be obtained. Because substance A, sorry, particle A settle, particle settle as slowly. See here, the terminal velocity. So for this DP1 to DP2, it cover only particle B, particle B, this area, which is why they say pure fraction of substance B can be obtained between DP1 and DP2. In the such range, oh, in the size range of the size range BP3 and BP4, a pure fraction of A can be obtained since no particle B settle as fast as the particle E. So DP3, DP4, only this one. See, DP4, DP3, only particle E. In the such range, DP1 to DP3, but A particle settle as rapidly as particle B. In the such range of DP2 to DP4, forming a mixed fraction of A and B. So between DP1 until DP3 and DP2 until DP4, so in the middle there are mix of fraction A and B. So for DP1 to 2, only B, DP3 and 4, only A. Tengok dia punya graf. Increasing density rho of the medium equation 30.1-24, the numerator becomes smaller proportionally faster than the denominator, and the spread between the PA and the PP is increased. Somewhat similar curve are obtained in the scapular region. Let's see that. Example 30.1-3, separation of a mixture of silica and galena. A mixture of silica and galena, possibly particle having a size range of 5.21 times 10 to the power of -6 meter to 2.5 times 10 to the power of -5 meters to be separated by hydraulic classification using free settling condition in water at 293.2 Kelvin. The specificity of silica is 2.65 and that of galena is 7.5. What is silica? Because of the specificity is the same. Calculate the size range of the various friction obtained in the settling. If the settling is in the laminar region, the crater friction will be reasonably close to the force spheres. The particle size range is dp equal to 5.21 times 10 to the negative 6 meter to dp equal to 3.5 times 10 to the negative 5 meter. This is size range for both mixture of A and B. Yeah. Density for P rho A referred to galena is 7,500 dengan 1,000. H2O is water. Density for the silica is 2650 kg per meter cube. Rho of water 998 293.2 Kelvin. So this value is from appendix A3, appendix A lah, dalam buku. The water viscosity also from that appendix at 290.2 Kelvin. So the value is available in the appendix. Assuming stock law setting 50.1-9 become as follow 50.1-29 yang BT tadi G gravity. B is the diameter of the particle A. Density for the component A in this case, which is the quartz. Salah, galena minus rho water over 18 mu of water. The largest number occurs for the largest particle and the biggest density, where dp A, the galena, and rho repeating into percentage 0.1-29, then we get 2.203 times 3 meter per second. Substituting into the Reynolds number equation, this equation, then you get 0.0547, which is Now that we know it is within the stock flow region or the laminar flow region, referring to figure 30.1-3 and using the same nomenclature, the largest size is dp4, 2.5. The smallest is dp1, 5.21, -6. This is -5. So the core fraction A consists of dpa4 to this value to dpa3. The particle having diameter dpa3 and dpb4 are related by having equal setting velocity in equation 30.1-26, repeating dpb4 equal to 2.5, equation 30.1-26, and solving for dpa3 equal to 1.26 times 10 power of 25 meter. Okay. So there are two material now. So this graph figure, it's only generally dp1, dp2, dp3. But since there are two material here, so there are dpa4, dpa3 refer to the material A. dpa3, dpb4, so this is material A, material B. dpb4 here, dpa3 here. Tengok graph ni. So dpa3, this is 30.1-26. 30.1-26. Yeah. 30.1-26. This is 30.1-26. dpa over dpb equal to rho pb minus rho over rho pa minus rho 0.5. When you can use this equation? When you have confirmed the NRE, or the real number is the laminar. So value of NRE is less than 1. Yeah. Then we can use this. Otherwise, we use this equation. Ini graph it. Yeah. Now the graph. Okay. Oh, wow. Okay. Ya, okay. Saya kita habiskan dan sambung pula. Okay, using 30.1-26 solving, then you get dpa3. At the moment, you have two, dp1, which is the smallest, dp4, which is the highest, that's one, the largest. So this dp1, dp4 is coming from the question. The range of the mixture A and B is between dp1 and dp4. Oh, yes. So the pore fraction of A consists of dpa4 to 2.5 something to dpa3. This one we already explained. So for dpa3, dp4 only particle A and the other. That's why they say the pure fraction of A consists of dpa4 and dpa3. But for the fraction, the diameter of dpa3, dpb4 are related to having equal setting velocity in blah 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 blah. And substituting dpb4 equal to this value. See dpb4, dp4, similar value. In order to obtain the value for dp3, dp3 ada value. Only dp1 and dp4. So to get dp3, then you use this 30.1-26, and you get dp3 equal to 1.26. This value. So this translation of POB fraction is dpb2 to dpb1. So dpb2, dpb1 here is specifically for particle B or material B. In this case, it's again galena. Sorry, silica. Sorry. Silica. The translation of POB fraction is dpb2 to dpb1 equal to into 1 K. The diameter dpb2 is related to dpa1 equal to this value by equation 30.6 and 1-26. Then we obtain the dpb2. So now that we know here dp2, dp3, then we can conclude the size range. So for this question, if it's asked, you need to show this size range as well. The size range of the first section of pure A is as follows. So for the pure A between this 3 and 4 is 1.26 to the 2.5. 1.26, how do you calculate it? Using equation 30.1-26. The mixed fraction dpb2, dpb4, dpa1, dpa2. So for material A, dp1 sampai dp3. See here. For material B, dp2 until dp4. So to get dp2, you use equation 30.1-26. Last range is the pure B here, dpb1 to dpb2. Okay, hopefully it's clear. You can refer to the recording later. Ada 9 minit. Stop kita. 4 lah. 4. Mechanism of sedimentation. When dilute slurry is settled by gravity to a clear fluid in a slurry of higher solid concentration, the process is called sedimentation, sometimes thickening. This is the batch sedimentation. A is the uniform suspension. After some time, the zone of settling after a given time. Then after some time, see compression of zone B or zone B and C disappear. So B, a clear liquid interface height V is height Z versus time of settling. Equipment for settling and sedimentation. Simple gravity settling tank. A simple gravity settler is shown for removing by settling a dispersed liquid phase from another phase. The velocity horizontally to the right must be slow enough to allow time for the smallest droplet to rise from the bottom to the interface, or from the top bottom to the interface and then coalesce. This is for the liquid. This is liquid dispersion. This is the for A. Cukup berapa panjang that allow dust to settle. plane A2. Next is the classification. The simplest type of classifier is one in which a large plane is subdivided into several sections, shown in figure 30.1-6. A slurry easily fit into the tank containing a size of solid particle. The larger, faster settling particles settle into the vacuum close to the entrance here. So the finer particle can go longer, can travel longer, and settle at the end of the classifier. Centrifugal separation. Centrifugal separator makes use of the common principle that an object whirl about an axis in the point at a constant radian distance from the point is effect on force. The object being whirled about the axis is constantly changing direction and is just accelerating. Even though the rotational speed is constant, the centripetal force acts in a direction toward the center of rotation. So you have centrifugal force, centripetal force. So centrifugal force is upward, centripetal force is inward. Sketch of the centrifugal separation. So slowly fluid, this one is moving, normally circular. So then the solid, because the wall is moving, so the solid will tend to be at the end of the wall, stick to the wall, but the liquid is here. Then there are separation of between solid and the liquid. Here we call it heavy liquefaction because the solid is not that dry. It's still liquid with the solid inside, but it's concentrated at the wall of the centrifugal. So we have light liquefaction, heavy liquefaction. If the object being rotated is a cylindrical container, the content of liquid and the solid exert one force per centrifugal force upward to the wall of the container. This is the first step process for settling or sedimentation particles through a layer of liquid or the filtration of a liquid through a bed of lubricated air inside a perforated rotating chamber. So in circular motion, the acceleration to the centrifugal force is A equal to R omega. AE is the acceleration from the centrifugal force in meter per second squared. R is the radial distance from the center of rotation in meter. And omega is the angular velocity in radian per second. So the centrifugal force Fc in Newton at the particle is given by Fc equal to MAE or equal to mR omega squared. So Fc equal to M. Okay, that one is for the English. This is for the SI. So this equation is 30.2-2. Swing omega equal to V over R, where V is the tangential velocity of the particle in meter per second. Then Fc equal to mv over R, and the rotational speed are given as n rev per minute. Okay. N is also a Newton, but this N is italic. Yeah? So italic N is referred to the rotational speed or revolution per minute. So we try to 2 pi n over 60. So n equal to 60 v over 2 pi r. Substituting equation 30.2-4 into 30.2-2, then we get 30.2-6. Bear in mind, n here refer to rotational speed, revolution per minute, not Newton. FC is Newton. This is rotational speed. Equation 30.1-2, okay, this is the gravitational force. In terms of the gravitational force, the cylindrical force is expressed by combining equation 30.1-2, 30.2-2, 30.3-3. So remember, there are other force acted on the particle. Okay, although this is focusing on the centrifugal force, there are gravity force downward. So take that into account, we get 30.2-7. So Fc over Hg equal to 0.00118 n square. Hence, the force developed in the centrifuge is R omega 2 over 3 or V square over 2 G time as large as the gravitational force. This is often expressed as equivalent to a certain amount of G forces. Example 30.1-2. Right. Any question? So thank you. Take attendance as well.
Okay, Doctor.
We continue next week.